So we're going to hide this instance of the vise, and we're going to go back up to operation 1. And we're going to start off with the stock visible for the first operation. Okay, we go to manufacturer, and we're going to create our new first setup. So we're going to do a new setup. And what I like to do is first set the stock. So I actually go to the stock tab, and we're going to do it from solid, which is our model. And we're going to pick down on model, down on the next tab, expand it out so that we can select our stock, the model of the stock. Okay, and that will give us our stock volume around the part instead of the entire fixture with the vise. Okay, so we're going to go back to the setup tab, and we're going to base our origin off a model box point. I'm sorry, a stock box point. But let's first get our orientation correct. We're not using model origin. We're going to use Z and X axis. We pick on the face we want normal to the spindle, and then we pick what's the X axis. It should be orientated like this with the red to the right. If it's not, you can move it by toggling this flip axis button. Now we're going to pick our box point. We want a stock box point. We're going to pick the one at the bottom. And some people prefer to put it at the top. I prefer to do it, base it off the fixturing, and there's less setup later for multiple operation parts like this. But you will need to put a 1, 2, 3 block in here in some cases to set your origin. Okay, so we finished that. Our stock tab should be fine. Now we're going to go to post process, and we're going to call this the 7312 is the part number, and this is operation 1. Okay, and we're going to comment. It's going to be op 1, and we're going to use work coordinate system 1, which will be G54 on a Haas. On the stock tab, I forgot to select the actual model, so I'm going to deselect that, and we're going to select our part number as the model. Apologize for that. Now we should be able to hit OK. So I'm going to go ahead and change setup 1 to be called op 1 so it matches what I'm calling it. And now we're going to do some pretty basic stuff you've probably done over and over. So we're going to do a face mill. We're going to select from our tool library. We're going to pick our face mill. Should be going about 3,000 RPM. If you have an older version of this tool library for the 24-25 school year, it might have a lower number in there. You want 3,000 or higher to get a better finish. Leave everything else at default. Geometry, we can take the default contours, and then we're going to go to heights tab. Our retract and our top height are both going to be based off stock top, and we're going to cut to model top. So if you have the correct model selected, the light blue and the dark blue is the difference of, and that's what the face mill is going to remove. We go to the next tab, and you can choose a pass direction. It's been my experience it typically goes the long way, which is how you'd want to do it. If you do have it go in a direction that puts force on the fixed jaw, that tends to be a little bit better. But we're doing such a light cut, I don't think it really matters that much. Our pass extension is 1.5 inches. I usually bump this up a little bit just to make sure that if our stock is oversized, we don't plunge right on top of it. Okay, and we're going to leave all this at default since we're only taking 30 thousandths off. We're going to do all that one pass. We don't need multiple passes on this side of the part. And then we're going to go to our linking tab, and we want the keep down, tool down selected. We want to lead in. Personally, I don't use vertical lead in races, but if you want to, go ahead. On older machines it has trouble, and I find it breaks tips of cutters often. So For this, there's really no reason for it. You're coming off the workpiece. And we're going to hit OK. Alright, so that we go down and we cut to the right. So you could flip direction. That puts the force on the fixed jaw. Might be able to run a little more rigid. I'm not going to worry about it for this light of a cut. Now, mill the top of that down. Now we're going to cut the perimeter of the part. There's a couple ways to approach this. You could use adaptive clearing. You could use just a couple contour cuts. We also want to think about separating the pocket on the inside as its own routine. The reason for that is it's a tight tolerance if you look at the drawing. This tight tolerance is designed to fit your pivot arm very tight so that it's got a nice slip fit. You want to set that up so that it's at a point in your program where you can stop it and measure. So you can either take one approach where you do it at the end, or you do it at the beginning and then you continue running. In this case, I'm going to do it at the beginning, and we need to pick a cutter that can cut this radius inside there. So what we're going to do is we're going to cut the interior of this with a 3/8 end mill, and what that will allow us to do is we'll cut the pocket first, and then it'll allow us to stop the machine and rerun that cycle if we need to before we proceed. Let's hide the stock because we want to select on the model itself. And rather than doing an adaptive, I'm going to just do a 2D pocket on this, and we're going to switch to the 3/8 end mill. Okay, we're going to leave this at default settings. For feeds and speeds, we'll go to geometry. We're going to select the interior of the pocket. You want to make sure your arrow is on the inside of the pocket. Now we're going to go to heights tab. And we've already milled this down to height, so we want to change our reference from stock top to model top, and for both of these references, because we've already machined 30 thousandths off, we don't want to waste too much time doing that. And we're going to go to the selected contour, and for that contour we're going to go negative 10 thousandths. That's to make sure that our pocket cuts all the way through. If we have a little bit of variance in flipping our part, and hopefully we won't get any like foil on the inside edge of that if we've set our tools right. Okay, we're going to go to the passes tab. We're going to do multiple depths. Our maximum roughing step down, we're going to set that at half the diameter, 0.18. It's 0.1875, but we're just going to put 0.18. We're not going to do any finishing step downs. We are going to do a maximum step over of 80% of the diameter of the cutter. If we had a really high speed spindle, we could use 20% engagement, but we don't have that, and you have to go a lot faster and you do lighter cuts. So we're going to go at 80% of our cutter diameter, so that is on a pocket. So it's 0.375 times 0.8 gives us 300 thousandths. So we're going to go a little bit bigger, so 0.3. And then we will use the morph spiral machining. That'll give us a little bit more efficient step over. Our multiple depths is fine when we have it. We're going to use even step downs. We're not going to do any finish passes in this case, because what I want to do is a separate finish pass, and that's all we'd run to adjust the size of this. Typically, if it's a looser tolerance, I would just go ahead and do a finish pass in this one routine. And we're going to leave, we'll leave the default 20 thousandths per side. Let's actually only leave that on the radial. So we're going to set the axial to 0, so it's going to go to full depth. We can go ahead and put on smoothing deviation. That will matter when it hits the corners. And then on our linking tab, we're going to leave all this stuff at the top on default. Horizontal lead in, we need that. Our sweep angle at 90 is fine. our vertical lead-in radius. Again, I don't tend to use them. There might not be enough room in this pocket for it anyway. Our ramp type, we'll go ahead and stick with helix. That way it goes in helical into the center. We don't really have to because it's a we're cutting aluminum and it's a 3-flute cutter. But if you get over 3 flutes, you kind of have to because the center of the ML doesn't cut. Ramp degree at 2 degrees. Maximum ramp step is the same as our step depth. And our ramp clearance height at 100 thousandths is fine. Okay, so we have our helical plunge, and then we have our cut, and then it'll do ramping plunges from then on. Okay, and it's going to lead into its cut. Alright, so that's our rough cut. It's leaving 20 thousandths around the outside edge. Now we're going to come back and do a straight contour. 2D contour. We're going to select the same tool. We're going to go to the geometry tab. We're going to select the same geometry on the bottom. On our heights tab, we're going to set these to model top on both. And our selected contour on the bottom, we're going to go that same negative 0.1. We're going to go to passes, where our compensation is going to be wear. Our finishing feed rate is going to stay the same. We're going to do, we're going to do what's called a roughing pass, but it's really just an additional skim pass. So we want to do that on this just so that we're getting a nice accurate hole without cutter flex. So we can leave the maximum step over alone because it's just going to be one pass. We're going to do multiple depths, and our roughing step down we're going to do is half a diameter of the cutter, 1.875, and we'll do one finishing step down at the bottom, 8 thousandths. It's going to go along wall. We're not going to, in this case, we're not going to finish only at final. We want it to have every opportunity to get rid of the cutter flex. We are going to rough the final depth. We're going to use even step downs. Order by depth only matters with multiple pockets. We don't need to worry about islands. We're going to scroll down, no stock to leave. We're going to turn on the smoothing so we get nice round corners. And then we go to the next tab. And we can leave most of this at default. Horizontal lead-in radius is fine. Sweep angle of 90 is fine. Linear lead-in distance is fine. It might not do one because there's not a lot of room in there. Vertical lead-in radius of 0. And I do believe I missed something on the other tab. Our step over, that's going to be left for the finished pass. We only have 20 thousandths of material here. So we're going to put 0.01, so we're going to take half of it on the rough cut and half of it on the finish cut. Go to the linking tab. Again, we're going to leave everything at default but take away that vertical lead-in radius. I hit OK. And then this gives us our 2 passes with a profile at the radius. So this is a lot of extra machining, but it is because the tolerance is tight on that pocket. The rest of this, we could have done it all together as the same routine if the tolerance was looser. I am going to rename this one 2D contour slip tolerance, slip tall. That way when it shows up in the code, we'll know that's where we want to restart our program if we measure this and we're out of tolerance. Okay, now we're going to go and cut the exterior. We're just going to do again another 2D contour. No reason to get fancy. This cutter should knock the corners off. Default feeds and speeds. Go to geometry, select the outer part of the part. And then we're going to go to heights. We're going to go from model top and model top. And then our selected contour is going to be where we're going to go to, but we're going to go a little bit deeper. Negative 10 thousandths. Now make sure you put 10 thousandths, not 100 thousandths, because we don't want to run into our vise. We're going to go to passes. We're going to do wear compensation. We are going to do roughing pass. Maximum step over there is fine. That brings our finish step over. So yeah, we'll just leave it at default. 37 thousandths is fine. And we'll go to multiple depths. Our depth of cut is going to be 0.1875 just to keep it consistent with the interior. We'll do one finishing step down at the bottom. 8 thousandths is fine. No wallpaper. We are going to finish the exterior at final depth. There's nothing crazy tolerance wise. We should have enough flute length. And we're going to rough the final. We're going to use even step downs. We don't need to worry about islands. And we don't need to leave any stock to leave. So when we go to our next tab, we're going to leave all this at default except for that vertical lead-in radius. And we're going to hit, and we want to keep the tool down. So we don't want it to pick up with each pass. I'll hit OK. And that should cut our exterior. Okay. And as you can see, the center of the cutter is well within the corner, so it'll knock the corners off of the part. Okay, what do we got next? We've got this hole here, this tapped hole. So we're going to go to a drilling cycle. We're going to select our tool, and we're going to use our library. And we're going to use a milling tool, which is a little unconventional, and we're going to use a 3/8 engraving tool. I'm going to select that. Sorry, 3/8 chamfer mill. Leave it all at default. We're going to go to geometry, and we're going to select just the cone of the countersink. It's important that that's all you select, or it'll go too deep. And then our heights, again, we're going to go from model top. So we've already milled the height down. Yeah, the top height is going to be the top of the hole. The bottom of the hole is going to be the bottom of the hole. And it should double check it, turn it sideways, make sure that the cone matches the countersink. That's what we want. Okay, then we're going to go to the geometry tab, and we're going to go to a deep drilling cycle, which doesn't PEX. Aluminum doesn't like to it doesn't like pecking. It doesn't like going straight down and holding the drill bit there. It wants to gall. And our peck depth, we're going to tighten that up to 0.06, a little bit wider pecs. And then we'll hit OK. Oh, I'm sorry, we need to go to the linking tab. We should be able to leave that all at default. Hit OK. Alright, so we got our drilling. Now we have this tool in the spindle, so let's go ahead and do our deburring with it now. We're going to do a 2D chamfer. Interesting. We're going to go ahead and select that tool again. See if it brings in our feeds and speeds. Not sure why that errored out. So here's our feeds and speeds. We're going to go to geometry, and we're going to select the outer perimeter of the part and the inner perimeter of the part. Make sure that our arrows are on the correct side of the line. And then we're going to go to our heights tab. And again, we're going to start off at model top. And our top height is going to be model top. And we're going to go to selected contours. And the next tab, we are going to go to wear compensation, and we're going to look at our chamfer settings. We want our chamfer settings to match what our drawing says. So our drawing says deburr all sharp edges with it says R, but it could be a chamfer break. It doesn't have to be a radius. It's 10 thousandths max, so we can't have that any bigger than 10 thou. So let's make it 9. So 9 thou, and hopefully we don't overcut it. And the chamfer offset and the chamfer clearance, I believe, can be set at default for this if the chamfer is not actually modeled. We go to linking tab. We're going to leave all this at default and hit OK. See what we get. Okay, so that should be just knocking the chamfer off the edges. Should be very light. If we don't set our tools right, and if we have a tool that has a busted tip, it'll go deeper than what our drawing allows for. That appears to have done what I wanted it to do. Fusion's chamfer tool works a lot better if the chamfers aren't modeled. It seems to be very unstable when you model the chamfers. I don't know why. It should just work.